So actually I've changed the title of my second talk slightly. So I'm going to talk about cup products and modular symbols. Other microphone.
You can test it.
Hello? Okay. So one thing I should correct something I said last time about cohomology. So if I have my local field, so if F is in the notation last time, if FV was a completion of a global field of characteristic not P at a prime in my set S, then the H2 of the absolute Galois group with coefficients in ZP1 is actually ZP if V is non-Archimedean and zero otherwise. So there's no Z mod 2Z case. I mean, it is true that if you take H2 GFV mu P infinity, or QP mod ZP1, then this is QP mod ZP if V is non-Archimedean, Z mod 2Z, or 1 over 2 Z mod Z, if V is real and P equals 2, and 0 otherwise. Okay, so right, so this talk I want to talk about something actually maybe slightly simpler. Oops, just one sec. Lost my page. Okay, so in this talk, let's let P be an odd prime, and I want to deal with a specific field for most of the talk. F is Q mu P. So, okay, so of course mu P is generated by a Pth root of unity, primitive Pth root of unity. I'll call it zeta P. And S now is the set of primes above P, so that's just the set, and there's no real places, so S is just this set. And okay, so I'm interested in the ring of S integers. So the ring of S integers is the ring of P integers, so it's the ring of integers with P inverted. And the units in this ring of P integers is isomorphic to a direct product of, so the P units is isomorphic to direct product of the P units of the maximal real subfield, and then the only new units you get when you go from the maximal real subfield to the whole thing is just the Pth roots of unity. Okay. So and the rank by Dirichlet's unit theorem of these units is P minus 1 over 2. Okay, so so inside the units, there's a nice group of subunits, subgroup of units, not subunits, consisting of those generated by 1 minus zeta P to the I for all I between 1 and P minus 1. And so this group is called the cyclotomic P units. It includes, it's easy to see, a Pth root of unity. Okay, so inside the P units we have the cyclotomic P units. And the index of, so let's call it, well, right, so I don't want to give this a name because I'm going to name its P completion. So the index of the cyclotomic P units inside the units is the plus part of the class number. Okay, so that's the order of the class group of F plus. And F plus is, of course, so here I used F plus. F plus is Q, you saw it before, zeta p plus zeta p inverse. Okay, so now I want to take p completions of everything, like I had in my last talk, so I can use cohomology, for instance. So EF will be the p completion of OFS cross. CF will be the p completion of the cyclotomic p units. And AF will be the p part of the class group of F. Okay? So the elements of p power order. Okay, so the Galois group delta, I'll call it delta. Galois group of F over Q is, of course, cyclic of order p minus 1. It's canonically isomorphic to Z mod PZ cross. And we can think of this Z mod PZ cross as the p minus first roots of unity in ZP. So this sits inside ZP cross. And this character, omega, is called the Teichmuller character. Okay. And right. So we can have two decompositions. If I have an A, which I have 3 of them over there, which are ZP delta modules, then I can consider two different decompositions of this ZP delta module. The first is I take, let's say that tau in delta is order 2, so it's complex conjugation, if you like. Then I can divide A as a direct sum of 2 subspaces where A plus minus is the set of A in A on which complex conjugation acts by plus or minus 1. P is odd, right? Okay, so we can do that. So if we do that, so that's the first sort of decomposition. Let me mention the second sort of decomposition. So I can also decompose A as a direct sum from I equals 0 to p minus 2 of A upper I. So where this is A upper I is the eigenspace for the, and I think you saw something like this in Samet's talk, for the ith power of the Teichmuller character. So delta, so it's A and A, such that delta A is omega delta to the IA for all delta and delta, or for the generator, if you like. Right, so we have this decomposition, and of course there's a relationship between the two decompositions. A plus minus is the direct sum I equals 0 to p minus 2 of I even if it's plus and odd if it's minus AI, right? So we're taking either the even characters or the odd characters, powers of the Teichmuller character, which is an odd character. Okay, so right, so now let's look at the decompositions of these particular groups. First under complex conjugation. So from what I've already said, we have the following relationship. So EF, the index of CF and EF is exactly the order of the plus part of AF, which is exactly the class number of the p part of the class number of F plus. Vandiver's conjecture, which you heard about in Professor Nquanto's talk. So Vandiver's conjecture is that AF plus is 0. Okay. So and it's known for p less than 163 million, Euler and Harvey, although there were previous computations also involving Euler, up to 12 million and 16 million, I think. But then they extended it. There's been many papers along the lines of extending this. Okay, so in fact, there's a relationship between the plus and the minus part. So if the plus part is non-zero, then it turns out that the minus part is non-zero. So in other words, if the class group is, the p part of the class group is non-zero, then the minus part is non-zero. Non-zero. I said non-zero. Wrote 0. Okay. So, right. And the minus part, this is by the analytic class number formula. The minus part is non-zero if and only if p divides the numerator of some kth Bernoulli number over k, where k is even and greater than or equal to 2. So bk here is the kth Bernoulli number, which is, if you like, the kth derivative at 0 of x e to the x minus 1. Okay, so it comes from this thing. Okay, so right, so that's by the analytic class number formula. Actually, there's various congruences, Kummer congruences, between these Bernoulli numbers. So, for instance, bk over k is congruent to bk plus p minus 1 over k plus p minus 1 mod p minus 1. So to say that mod p, so to say that p divides the kth Bernoulli number over k is to say that it divides this one, and conversely. So it's so here, so we can restrict to in determining whether p divides the order of the class group, we can restrict to k between 2 and p minus 1. But actually, it never divides. It actually divides the denominator of bp minus 1. So we can actually restrict to p minus 3. And then we can actually do slightly better than that, I suppose. Right. So, for instance, I mean, you have to go up to the 12th Bernoulli number before p even divides 1, and it's a result of Kurihara as well. Okay. So now.
So, Romyar, when you say this is the analytic class number formula, this is, I mean,
Well, with generalized Bernoulli numbers.
But I mean, this is not the Herbrand-Ribet theorem?
No. So Herbrand-Ribet theorem is when you divide it up into eigenspaces. When you look one eigenspace at a time.
Okay, you're saying the whole thing.
Yeah. So, right. Okay. So now if we look at eigenspaces, so say k is even, 2 less than or equal to k less than or equal to p minus 3, let's say. Note that right, ak 0, which is just aq, is 0. Okay. So okay. So now I'm going to look at the. So I have dim. Maybe here I could use p minus 1, but anyway. So the fp dimension of a f k. So if I look at the kth eigenspace mod p, this is less than or equal to the fp dimension of the 1 minus kth eigenspace mod p, and that's less than or equal to the fp dimension of the kth eigenspace mod p plus 1. So this is the reflection principle, or Spiegelensatz, and so I guess this is due to Leopold. So in particular, if some even eigenspace, which is in all known cases, right, is 0, then the corresponding 1 minus kth eigenspace is cyclic. right? Because this FP dimension is at most 1. Okay, so in all known cases, these groups are cyclic, the odd eigenspaces. Okay, so Mazur and Wiles actually, so Herbrand-Ribet, maybe I should say first, tells you that one of these eigenspaces is non-zero if and only if P divides one particular Bernoulli number. So,
okay, so your if and only if there is P divides BK for some K? What is
yeah, for some K even, yeah. Yeah, certainly not all.
Yeah, I didn't.
Yeah. Right. So AF 1 minus K is non-zero if and only if P divides BK. Okay. This is notice these numbers only depend mod P minus 1. So this thing is the same as P minus K. Maybe if that's more comfortable. Okay. So let's see. So this is Herbrand-Ribet. But as a consequence of the main conjecture, you can actually say exactly what the order of this eigenspace is. So it's P to the p-adic valuation of B1 omega to the K minus 1. So this is so B and chi is a generalized Bernoulli number, and it's defined in some similar way with involving a sum of characters to a Bernoulli number using functions like that. So actually you can explicitly determine the order of this eigenspace, although it's not clear whether, right, I mean, that doesn't tell you whether it's cyclic or not, just the order. Okay, so now as for the eigenspaces of EF, well, the odd eigenspaces, right, are 0. I said that K, except for the K equals P minus 1, this is because K is not P minus 1. And the P minus first, you would get the first eigenspace is mu P. And then the even eigenspaces are isomorphic to ZP. And again, I think this was in maybe your talk, or whose talk was it in? It was in someone's talk. Okay. So, right. So the even eigenspaces are isomorphic to ZP. And so in particular, because CF has a finite index in EF, CFK is also isomorphic to ZP. And it's generated by a particular unit, which I'll call eta P minus K, particular P unit. So what is eta P minus K? Eta P minus K will be the projection of 1 minus zeta P to the P minus 1 power to this eigenspace. So how do I do that? I take the product over delta and delta of 1 minus zeta P to the omega delta. Notice this is some p-adic number, but it makes sense to raise it to that power because I'm working mod P here. And then it makes sense again to raise to a p-adic power on the outside here because I've taken the pro-P completion, so I can raise to ZP powers. Wait, let me make sure I put the right power here. So minus K. So normally I'm going to deal with eta I, and then and that would be omega delta to the I minus 1. And hopefully that matches up. Yeah. So yes. Okay. So so now that's what I wanted to say about these objects. Now we can consider cup products. So remember last time EF was actually isomorphic to H1 GFS ZP1. And H2 fit in an exact sequence where here I have AFS, if you like. So here I would have AFS. So that would be the S part of the class group. I called it XFS to denote as a Galois group. And then I had some direct sum V in S. There's no, where P is odd, so just ZP. And here's a V non-Archimedean. And then ZP and then 0. So last time we had this. But in this case, this is the class group modulo the primes in S, the P part of the class group modulo the primes in S. Prime in S is principal, right? It's generated by 1 minus zeta P. So modding out by that element doesn't change the class group. So this is just AF. And now we only have one prime in our set, so this is just ZP. And this is an isomorphism. So in other words, our H2, is isomorphic to AF. Okay? So H1 is EF and H2 is AF. But this is H2 with ZP1 coefficients. And that's not the H2 I'm going to be interested in. So I want to consider cup products like this. So ZP1, and then I want to take the same group, ZP1, and then take this to ZP2. Last time we considered, in constructing the S reciprocity map, we considered where this group was ZP1 and these coefficients here were ZP. But now I'll take them both to be ZP1. This is, you should think, analogous to the norm residue symbol in local class field theory. Because if I took, instead of GFS, I took GFV, then it would be the norm residue symbol. Okay? So, well, if I took it mod P to the mod P, for instance, then it would be the Pth norm residue symbol. Okay, but I mean, it is the norm residue symbol. So, anyway, the point is that what does this give you? So this gives a pairing. And now I don't want to look at this pairing on all of the P units. I'm only going to be interested in it on CF. So this gives a pairing from CF cross CF to H2. Now, one word about this H2. So if I take it mod P, right? So mod P, H2 GFS ZP2 mod P is actually, because GFS has cohomological dimension 2, because P is odd. That was the mistake last time. Okay, so because this has cohomological dimension 2, and there's no real places, this thing is actually isomorphic to GFS mu P tensor 2. If you like, ZP2 mod P is mu P tensor 2. Just a different way of writing it. So this group, but now F acts trivially on the Pth roots of unity because F contains the Pth roots of unity. So this group is actually H2 GFS mu P tensored with mu P. And this thing is the class group mod P by the argument I just gave. So tensored with mu P. And then, of course, I don't really need to write mod P anymore. So it's this is non-canonically isomorphic to the class group mod P. Or if I choose a Pth root of unity, then it's isomorphic to the class group mod P. So mod P, this is the class group mod P. But I want to take it to the whole group, in which case it could, the pairing to the whole group, in which case the H2 could be different. Okay, So what are the properties of this pairing? So one is it's antisymmetric because cup products are antisymmetric. Two is that it's Galois equivariant for the action of delta. It's bilinear, of course. And then it has one other nice property, it turns out. And that is that x comma 1 minus x equals 0 if x and 1 minus x are both, in fact, if they're both, well, we're only defining it on cyclotomic p units, but this has nothing to do with it being cyclotomic. It's just on p units. If x and 1 minus x are both p units. Okay, so those are the properties. So let me point out some examples of where you have this fourth thing happening. So zeta p, of course, if I take zeta p to the I, that's going to pair trivially with 1 minus zeta p to the I. But if I is prime to p, then the I doesn't, so this will be 0, right? Because that's a good x. But this means that zeta p pairs trivially with all the 1 minus zeta p to the i's. It also pairs trivially with itself, where you could use, for instance, the antisymmetry. So in particular, zeta p pairs trivially with all cyclotomic p units. Okay? So my pairing on CF actually is determined by the pairing on CF plus, if you like. Right? That determines the pairing completely. Okay. And because it's a pairing on CF plus, and it's Galois equivariant, right, it actually lands in the plus part of H2. So it's a pairing to the plus part. Which is good because, I mean, if we work out what this, let me now write pluses here. Plus, so mod p, the plus, now I pulled out, right? I have to put a plus on the outside, but mu p has minus 1 action of complex conjugation, so this becomes minus in order to make the whole thing plus. So minus, minus. So this is a pairing to the part of the class group mod p, which we actually know is non-zero sometimes. Okay? So that's good, in a way. Unless you're studying Vandiver's conjecture. So, right. So there's more complicated expressions where you can find cyclotomic p unit plus cyclotomic p unit equal 1. I'll write some out for you here. Okay, so for instance, let me make sure I write it in the way I need it later. Okay, so that was example 1. So example 2, 1 minus zeta p to the u over 1 minus zeta p to the u plus v. So now I take 1 minus zeta p to the v over 1 minus zeta p to the u plus v. And now if I put zeta p to the u here, and I put plus, then I'll get 1. Okay? So this means that this p unit pairs trivially with this one. I can ignore the zeta p because of number 1. So I get 1 minus zeta p to the u over 1 minus zeta p to the u plus v paired with 1 minus zeta p to the v over 1 minus zeta p to the u plus v equals 0. Okay, now let's just, for simplicity, write x uv equals 1 minus zeta p to the u, 1 minus zeta p to the v for any u and v. So then what is this saying? It's saying that x uv minus x u plus v v minus x u plus v equals 0. Because you see this there's four things, right? I'd use bilinearity. So it's this paired with this, this paired with this, this paired with this, this paired with this. But this pairs trivially with this because it's antisymmetric. So this is XUV is that sum. Okay? So that's 2. And then 3, just for, you can modify this very slightly. So, oh, but I just modified it. This is not what I... Oh no, it must be what I want. Okay. So 1 minus, so if I take 1 plus zeta p to the u over 1 minus zeta p to the u plus v, and 1 plus zeta p to the v over 1 minus zeta p to the u plus v, and then I take minus zeta p to the u, then hopefully, yes, okay, this is 1. And so then I get some similar pairing as 1. Notice the plus is fine because this is 1 minus zeta p to the 2u over 1 minus zeta p to the u. So if you work out what this tells you, it tells you something rather awful. X 2u 2v minus x u 2v minus xv 2u plus 2x uv minus x 2u u plus v minus x u plus v 2v equals 0. Okay, so you have something like this when you work it all out. And I think you have to apply 2 to get that form. Okay, so so you see you can impose certain relations on the values of the pairing using these. And in fact, you can use these to impose relations among the eta I, eta k minus I for, let's say, varying I and fixed k. Why would I want to fix k? Because if I fix k, then this thing lies in a particular eigenspace. This has a omega to the 1 minus I action, and this has an omega to the 1 minus a k plus I action. So overall, this lies in the following eigenspace of A. Oh, sorry, it's in H2. So this lies in the following eigenspace of H2, H2 GFS ZP2 2 minus k. So I can look at all, these are all the pairing values. These will determine the pairing projected into this eigenspace completely. Okay, so I can use these to impose relations, and then that narrows down the possibilities for the values of the pairing. So that's what Bill McCallum and I did some time ago. This is our paper in 2000, appeared in 2003. So here was our theorem. This is a computation. So there exists a unique up to scalar unique up to scalar non-trivial pairing, maybe I'll just call it sub k, from CF cross CF to AF, or maybe I'll just say no AF, to the Z mod, to mu p tensor 2 minus k, for each odd prime p, so the scalar is in fp, for each odd prime p and even k to k between 2 and p minus 3, such that p divides the kth Bernoulli number. So you see, for all such p and k, the eigenspace for such a p and k, which is called an irregular pair, okay, so p divides the 1 minus kth eigenspace of the class group. Okay, so remember that our pairing, mod p, was a pairing to AF 1 minus k tensor mu p once we project it to the 2 minus kth eigenspace. So the point is here that AF 1 minus k tensor mu p is actually isomorphic to mu p tensor 2 minus k for such pairs because p is less than 163 million. Okay, so it's cyclic. Okay, so mod p is just mu p. Okay, so there exists a unique non-trivial pairing. The problem is, so satisfying, oh, I didn't write a lot of the conditions, did I? That satisfies that it is antisymmetric, Galois equivariant, bilinear, and x comma 1 minus x equals 0 for x equaling, I need a particular value of x, 1 minus zeta p to the a over 1 minus zeta p for all even a or something like that. That's an allowed value, not equal to. Even a. Maybe we'll just say for all a, not 1 mod p. Okay, so we couldn't impose all the relations because we can't find all the relations, but we know at least that if we impose these relations, that's enough to knock down the possibilities for the pairing to a single dimension. Okay, but what it doesn't show you is that the pairing's non-zero. Okay, but then of course since in each case for an irregular pair we found such a non-trivial pairing, and in most cases for a regular pair we found a zero pairing, we made the conjecture when we imposed these relations that that this pairing or the span of the image of the pairing is all of H2, the plus part. So essentially the cup product is surjective, right, on cyclotomic B units. So right, so this suggested that to us. Okay, so then later on I proved the following theorem, that this is true for p less than 1,000. And this used a bit of Galois actions on the cohomology of modular curves. And more recently, so this was maybe 2007 or something that it appeared. Then more recently, and it's not appeared yet, but it's the paper is submitted. Fukaya and Kato proved that it's true for p less than 163 million. Of course, that's not what they proved. That you won't find that statement in their paper anywhere. But okay, so we'll see why in the next talk. But I will say something that they proved in this talk and how it relates to the homology of modular curves. So in this talk, I want to go in one direction, which is from the homology of modular curves to the setting we have here. And in the next talk, I want to go in the opposite direction. Okay, so whatever that means. So let's talk about the homology of modular curves.
So your conjecture is equivalent to saying that the cup product pairing you defined before reduces mod p to this pairing?
Right, yeah. So, well, the cup product pairing does reduce oh yeah. Right, yeah. Of course, this pairing is only up to scalar, but yeah. Up to scalar, right. Right. That's right. Okay, so so just run quickly through some of the usual things. H is the upper half plane. And we have a congruent subgroup of SL2Z, gamma 1p. So this is the matrices A in SL2Z that mod P look like upper triangular unipotent. Okay. And the quotient of H by gamma 1p is the open modular curve. So yeah, I guess I should say how, so SL2Z acts on H by A, B, C, D times Z is AZ plus B over CZ plus D. Okay. So we take the quotient. That's an open modular curve. And if we extend the upper half plane to by throwing in the points in Q and a single point at infinity, then the same formula essentially gives you an action on this. So we get we can consider the quotient, and this is the closed modular curve, and this is a compact Riemann surface. And now I'll just introduce some non-standard notation here. So C1p will be the cusps. So if I just consider, so it's the complement. So if I consider the quotient of P1Q by gamma 1p, that's x1p minus y1p. So that's those are called cusps. Okay, right. Okay, so now what I want to consider is homology, H1, in the sense of algebraic topology, of x1 of p relative to the cusps. And because everything has been ZP so far, I will just take coefficients in ZP. Okay, so we want to consider this group. Okay, so this is relative homology. Okay, so what is this group? So it's generated by modular symbols. So what are modular symbols? Those are just, so I take two cusps, so I need to find paths between one cusp and another cusp in x1 of p. So what you do is you find that path inside H, right? So let's say I have two cusps here, alpha and beta. There's some rational numbers. Then I choose any path in H star, the interior of which is in H from alpha to beta. And usually one typically takes the geodesic for the hyperbolic metric there. And you call this thing alpha beta. Actually, what you call it is you take the image then of that path inside this group, and that's called alpha beta. Okay? And we can also do this with infinity. You just imagine a line going out to infinity. Okay? So it's generated by modular symbols alpha beta, where alpha and beta are in P1Q. Okay. Okay, so that gives you a set of generators for this group as a ZP module. But there's a much simpler set of generators than this one, and a simple presentation of this group on these generators. So this group has a simple presentation as a ZP module on generators. So I'm going to call them UV, square brackets colon with a colon there, with U and V in Z mod PZ, not both 0. Not both 0. Okay, this might look familiar to you if you were thinking about the cyclotomic units. What is the presentation, in fact? So with relations, okay, UV equals minus U minus V equals minus V U equals U plus V plus U plus V V. Those are the relations. Okay, and that gives the presentation. So the usual thing to do is just to take UV to be the path from, so you take a certain matrix, and then you take the path from A over C to B over D. Take a certain matrix in SL2Z. I'm going to modify that slightly by applying an Atkin-Lehner involution at P. So we take, and it works just, it has the same relations. We take UV to be the more complicated minus D over BP minus C over AP, where ABCD is in SL2Z, and U is just C mod P, and V is D mod P. D taken mod P. So you can always find such a matrix, and it turns out that the class of this path is independent of the choice of matrix. Okay, so this group actually has actions of Hecke operators. So for instance, TL, L prime not equal to P, any Tn, but we give a separate name to the pth Hecke operator, and then maybe a diamond operator J, where J is in Z mod PZ cross. Okay, so we have Hecke actions there. So let me briefly say how the Hecke operator acts on an element of H star. So TL alpha is simply I equals 0 to L minus 1. I hope I got this right. 1I L alpha plus L 1 diamond operator alpha, where the diamond operator acts by diamond operator L alpha acts as A times alpha, where A is a matrix which is congruent to L inverse L mod P. And then the UP is the same thing, but now we take this. Okay. So this gives you actions on the homology by acting on these modular symbols right at the same time, on the two coordinates at the same time. Okay, I'm not going to describe what the action is on the Monin symbols, but you can actually write out formulas for how these operators act on them. But I will describe maybe the action of one Hecke operator on the Monin symbols. So first, what I want to do is not deal with the whole space anymore. So let's deal with the following subspace. x1p zp sub 0, which I'll define to be the zp submodule generated by the uv where both u and v are non-zero. Okay? So this thing actually contains the usual h1, and it's contained, of course, in homology relative to the cusps. Okay, so this is actually preserved by the Hecke operators. So we have Hecke action here, right? So we're good. Okay, so now I want to take not the whole of this group, but rather I want to take, I also have complex conjugation here on the upper half plane. How do I think of that? So induced by, so on the upper half plane I think of it as z goes to minus z bar. Okay? And then, right, so if I take the plus or minus eigenspaces, so this gives me, so plus minus 1 eigenspaces, this gives me modules h1, x1, p, zp, 0, plus minus. Okay. And so, so the projection, so if I project my operator here, how does, I guess I should say how it acts, right? So on a uv, it takes it to minus u comma v, so over 2. So now that's the projection. So this is in the plus part. And yeah, if I put minus, then it would be a minus here. And now this, so of course these satisfy one more relation, that uv plus equals minus uv plus. So it's so this group has a presentation with these this relation and these relations here with pluses. Okay, so now let me explain the relationship with cup products. Okay, so so remember that xuv was 1 minus zeta p to the u, 1 minus zeta p to the v, right? And there's a few obvious relations that I didn't mention last time. Because zeta p pairs trivially with everything, I can write this, you see, I can write 1 minus zeta p to the u as zeta p to the minus u minus 1 times zeta p to the u. And so minus zeta p to the u times 1 minus zeta p to the minus u. So xuv actually equals x minus u v. Looks like that, right? And that actually equals x minus u minus v. And if I flip the symbol, that's going to change the sign, so that'll be minus x vu, which is almost the same, but of course this is minus x minus vu. So you see that these already satisfy all the relations except for uv equals this. And but we saw that from the relations 2 that in fact it satisfies that as well. xuv equals xu u plus v plus x u plus v v. Sorry. Yeah, that's right. So it satisfies all of these relations. Therefore, I can define a map, because these relations give a presentation of this group. I can define a map as follows. So this is a var pi. Okay. So define pi from h1 x1p zp plus 0 to h2 gfs zp2 by var pi of uv Now u and v are both non-zero, which is important because I'm going to take 1 minus zeta p to the u, 1 minus zeta p to the v. Right? And that makes sense because those numbers only matter mod p. And since it satisfies all the relations, I have such a map. Okay, so now, right. So the conjecture of myself and McCallum is now equivalent to var pi is surjective. Right? Because this image is the pairing values. Okay. So, but we saw that the pairing values satisfied more relations than just the ones I've used. There were the third set of relations. So the question becomes, do these things satisfy those relations? Well, no. But obviously the map is going to factor through the quotient by those relations. So let's see where those relations come from. So it turns out that if I take diamond operator inverse T2, so if you like it's the adjoint Hecke operator, and I apply that to UV, then I get U2V plus 2UV plus U plus V 2V plus 2U U plus V. So a computation gives you this. And let me also point out that if I take 2 inverse UV, this actually gives me 2U 2V. And that's because I applied the second lane revolution. So I have the inverse here instead of the usual thing. Okay, so now if I take var pi of 2 inverse times T2 minus 1 minus 2 diamond operator 2 applied to UV, then I get something which may or may not look familiar. U2V plus X2VU plus X U plus V V plus X2U U plus V. This must be a 2V. It's a 2V. Minus 2XUV minus X2U 2V, which was what appeared in the third set of relations. So that's 0. Okay, so this thing is actually, well, so what is this? So this is the second Hecke operator. And 1 plus 2 diamond operator 2, if I apply any power of the Teichmuller character to the numbers that appear here, remember these diamond operators generate a subgroup of the Hecke algebra, which is a Z mod PZ cross mod plus or minus 1. So if I apply some even power of the Teichmuller character there, then I get something which is the second coefficient of an Eisenstein series. And so now I'm taking T2 minus the second coefficient of that Eisenstein series. Or actually now here I'm taking several at once because I haven't applied a character there. And so here's what the conjecture was. So Buzyok also came up with essentially this conjecture independently. So right. So our conjecture. Oh, and we could do a similar computation with T3. And there's another set of relations that gives you that. And then we couldn't find anything more. But nevertheless, we conjectured that var pi is Eisenstein, which is to say that var pi Tx equals 0 for all t in some I, where I is some ideal, if you like, of, I didn't define any Hecke algebra, but you could take the formal Hecke algebra over with ZP coefficients if you like. So I is the ideal of the Hecke algebra generated by TL minus 1 minus L diamond bracket L and L not equal to P and UP minus 1. Okay, so in other words, what we get is a map from H lower 1 x1p zp 0 plus mod I to H2. And now the nice thing is, once this Eisenstein ideal is ordinary, but anyway, once we're in the ordinary part, this 0 doesn't matter. So it turns out that this thing is actually just H1 x1p zp plus mod I. Okay. So we could have just restricted to the usual homology, but it's harder to describe what that is in terms of the Monin symbols. Okay, so right. So again, so there's a theorem. This is a theorem. This conjecture, I said it as a conjecture, but really, I should have just stated it as a theorem. So theorem. Fukai Kato. Or pi is Eisenstein. So, so why is this? So in the introduction to my paper, I actually said why I thought this would be true. And the reason is that so each cyclotomic unit, you have these units on the open modular curves, which are Siegel units. And the cyclotomic p units are specializations of these Siegel units at cusps. In particular, if you choose the right one, you can get them as specializations at the cusp at infinity. So, Kato has an Euler system of these cup products of Siegel units, which are called Bailenson elements. And it turns out that, so the way they prove this is that they construct a map from this homology group to some cohomology group of the modular curve, second cohomology group, I guess, over Z1 over P. But anyway, the point is they construct some map which takes a Monin symbol to a Bailenson element, and then so they construct a map that way, and then this map var pi that we're constructing here is just the composition of that map with specialization at the cusp at infinity. And it turns out that the specialization at the cusp at infinity is Eisenstein. Okay, so that's where the Eisenstein comes from, specializing at infinity. So, okay. So let me just say one last thing. So you can do this, of course, not just in level p, but in level p to the r, and the same conjectures are made, which are actually, the conjecture of McCallum and myself is actually equivalent to the conjecture I stated. If you go to zeta p to the r, q mu p to the r. Notice this conjecture does not imply the conjecture of McCallum and myself. So for that, that'll be discussed in the next talk. So you can make these, you can define a map on inverse limits. These things are actually sort of compatible under trace maps and norm maps. So you can actually define a map on the inverse limit of these homology groups and the inverse limit of these things under norms. And so you can do all kinds of great things. But maybe I should say, originally I was talking about the values Bill and I computed were these pairing values. And so let me just point out so what does this pairing value correspond to under this map var pi, well, under the inverse of this map var pi? So this somehow is supposed to correspond to, well, you're going to get some sum, right? So you'll get some sum that looks like p minus 1 times omega delta to the I minus 1, 1 minus zeta omega delta, 1 minus zeta. And then we should project this. Maybe I'll just write, we project this to the 2 minus kth eigenspace here. Okay, because this lies in the 2 minus kth eigenspace. Oh, sorry, this equals this, of course. Okay, so if you imagine what's mapping to this, right? It's sum of symbols p minus 1, omega delta to the I minus 1, omega delta 1 mod some Eisenstein ideal for 2 minus k or whatever. It's really not 2 minus k, but anyway. So this is actually so this actually then, if you imagine that you map to some lattice for some cusp form which is congruent to the Eisenstein series g2 omega to the k minus 2. So that's why it shouldn't really be 2 minus k. So if you have an F, and let's say it's congruent mod p, so this is some cuspidal eigenform here. And this is some prime over p, so this is the coefficients are congruent. Then this thing actually corresponds to a reduction of a certain L value, LPF omega to the I minus 1 mod Eisenstein. So whereas the pairing values 1 minus zeta p to the u, 1 minus zeta p to the v correspond to these Monin symbols, these pairing values, a to I, a to k minus I, correspond to L values of cusp forms that are congruent to Eisenstein series, or at least sort of all interpolated at once, because there may be more than one F. But so L values of cusp forms that are congruent to Eisenstein series reduced mod the Eisenstein ideal in an appropriate lattice. So this is actually how I first thought of this conjecture before I thought of it in this way. So anyway, that's what I want to say today. Thanks.